our spring colloquium series with a candidate for the position we opened this year in the physics department. And it is a great pleasure to welcome Professor Mathew White from the Johannes Kepler University in Linz, Austria. Before moving overseas, Professor White actually graduated from here in the United States with a BS at the University of Washington in Seattle and a Ph.D. at the University of Colorado in Boulder. And before becoming a professor in Johannes Kepler, he completed a postdoc position at the Linz Institute for Organic Solar Cells. And that's what he's going to talk to us about, thin film organic optoelectronics. So before he starts, we actually want to give him our usual token of appreciation for visiting us. This is something we do for all our speakers coming here, and it's a small token for fighting the cold here in Johannes. Thank you very much.
Great. Okay, so thank you, Mathew, for the introduction. Thank you all for being here. As she mentioned, my name is Mathew White. I'm from the Johannes Kepler University in Linz, Austria. The title of my talk today is Thin Film Organic and Hybrid Optoelectronics. So just as a little bit of an introduction, not many people are familiar with the city of Linz. So it's a little town right here on the Danube River, right between Vienna and Salzburg in northern Austria. So we're very close to the Czech border and the German border. We have a nice downtown main square. We're famous for cake, Linzer Torte. And this building down here is our University Technical and Natural Sciences building, and we have a pond and a campus that's kind of unique for European universities to have a real university-style campus. So to outline my talk, I'm going to give a brief introduction to organic semiconductors and devices that we can make from them. And I know a lot of people, I remember being beginning a Ph.D. student in physics and not having a clue about organic semiconductors or chemistry at all in general. Then I want to give you some motivation for what we might want to do with these materials and why they might be good or better than conventional semiconductors for certain applications. And then talk about some results that I've had over my research career. Starting with air-stable selective contacts for devices, moving on to alternative substrates, and then talk about what next steps might be appropriate for organic semiconductors, specifically for photovoltaics. Okay. So organic semiconductors refer to molecular materials that are made from carbon. And carbon can typically take two hybridization states. There's the sp3 hybridization state, which forms tetrahedral configurations, which forms diamond, and polyethylene, which are generally insulators. But the more interesting form for us is what's called the sp2pz hybridization, which has these three in-plane orbitals which form hexagonal 120-degree packing structures, which is used in, or which forms graphite and graphene type structures. And then there is this out-of-plane pi electron, which is interesting and useful for us. And so these type of organic semiconductors are classified generally into small molecules, which are typically vacuum processed, but can also be solution processed, as is often done here in the department in physics. And also into polymer type devices. So polymers are long chains that are not so tightly confined, and they can be of intermediate or extremely long lengths. And they group these together with fullerenes for a reason that I will describe later. They're often combined together in photovoltaic applications. And so when we draw a chemical structure, we typically draw a single bond, double bond configuration. We call that a conjugation along the material. And the double bond that's drawn here is the pi bond. So this is the interesting one. And the sigma bonds hold the structure together, whereas the pi bonds are a little bit more free to move along the structure while it's held together by the sigma bonds. But if we draw this polyparaphenylene, it can take two configurations. It can be in this aromatic configuration or this quinoid configuration. and it's roughly equivalent. Each pi electron on each atom bonds with one, either the left leading or the right leading nearest neighbor. But this quinoid configuration is a higher energy configuration, roughly 100 MeV per repeat unit. And so to optically excite from this configuration to this configuration requires energy, and the associated pi electron redistribution is on the order of optical visible energies. So when we shine light into these materials and rearrange the distribution of these pi electrons on the molecule, for a small molecule it's pretty evident that we rearrange the distribution, but we don't really create a charge on that molecule. We just redistribute the electron density. And since these molecules are very small, roughly 1 nanometer in the longest direction, they are tightly, the positive charge and the negative charge feel the influence of each other very strongly. So this forms not a free carrier, but what is called an exciton, a tightly bound Coulombic quasi-particle, and that is neutral. And so if you apply an electric field, it doesn't move because the positive and negative charges move in parallel. And so on a polymer, you get the same thing. You wind up that there's this dislocation, a change in the orientation of the pi electrons. But even if the positive and the negative charges were separated as far as they could be, separating them further would cause a drastic increase in the lattice energy, which doesn't happen. So these things feel a lattice and a Coulombic confinement, which render them in excitons, tightly bound excitons. So if we want to photo-induce useful charge carriers, we need to do what's called photo-induced charge transfer. We have an acceptor molecule, a separate organic semiconductor, and that's why I lumped polymers with fullerenes, because this C60 fullerene is the most commonly used acceptor molecule. So you photoexcite an exciton on the polymer, but if there's an acceptor molecule near to it, the electron can transfer to it, leaving behind a positive charge on the polymer and a negative charge in the fullerene. And these separated charges can then be used. These exciton states have a lifetime on the order of 100 picoseconds, but the charge-separated states have lifetimes on the order of microseconds. So this extra time that you buy at the cost of the energy gives you useful time to extract the carriers and make solar cells out of them. And once you have free carriers, whether they're photoexcited, or whether they're injected, or chemically doped, or electrochemically doped, the transport along the semiconductor molecule is limited by the molecular size. And so to get from one molecule to the other, you need to have all other processes, and this is generally described as hopping transport. So you have hopping from one molecule to the other, then you can imagine that these molecules pack nicely, but at some point there's a grain boundary, and you have hopping across those grain boundaries. So whether it's intra-crystal crystallite hopping or intercrystallite hopping, the limiting transport mechanisms are definitely not on the single molecule, but hopping from one molecule to the other. So you have a semiconductor here, or a material that behaves like a semiconductor, but the optical properties are derived largely from the molecular structure, but the electrical hopping and transport properties are derived from the crystal packing in general. This is an example of pentacene up here, which is probably the most well-studied organic semiconductor in the history of organic semiconductors. And when pentacene packs into a crystal, it forms van der Waals crystals, and it forms this kind of loosely packed and not very cofacial herringbone structure here. And so this TIPS pentacene is one example of molecular engineering where you add on these bulky side groups, which intuitively would say we're taking up volume with useless junk. How can this make the device better? But because the crystal packing is so much closer and more cofacial, you can actually improve the mobility and conductivity in the pentacene. And so that's just a brief introduction to organic semiconductors. When I describe hybrid devices, I mean a device that's made from an organic semiconductor and an inorganic semiconductor in some configuration. The organics and the inorganics can have different functions, but that's just a terminology that's poorly defined to describe systems made of inorganics and organics together. So talking about some of the devices that we can make from these semiconductors. Optoelectronic devices that I'm particularly interested in are solar cells and LEDs. So the basic function of a solar cell is we have a semiconductor with two contacts, one near the conduction band and one near the valence band. And we optically excite, we promote an electron from the full valence band into the empty conduction band, and we can harvest the carriers driving through an external circuit and get useful power out. An LED, in essence, is the exact process in reverse. So we just inject an electron into the empty conduction band, and we inject a hole into the empty or the full valence band. They recombine and emit useful light for displays or for lighting. And both of these are diodes, so they should somehow have a current as a function of voltage response that resembles a diode curve. An LED in forward bias will emit light. That's where you're injecting carriers. If you're injecting holes and electrons, then they will recombine and hopefully emit light. A solar cell in the dark will have the same type of curve. It's just a diode. When you shine light on it, you wind up shifting the whole curve downwards, and so you get a photocurrent at zero applied bias. And what this does is it sets up several parameters that we should define before we really start talking about solar cells. So that short circuit current, the value of the current at zero applied bias, is the value of current that if you took a solar cell and took two wires sticking out of it and just shorted them together and shone light on the solar cell, how much current would flow. And that's this value here, the short circuit current. If you then snip those wires, current will flow until it builds up a potential that stops the current flowing from within the solar cell. That's called the open circuit potential here. Now, the value of power that you get out is equal to the product of the current times the voltage. And so in this quadrant down here, you have negative current and negative voltage, and you have positive power, which means you're burning power. And up over here, you have positive current and positive voltage, so the product is positive. But in between, you have positive voltage and negative current, which means you have negative power, which means you're generating power. And at some point, there's a maximum. At zero current and zero voltage, you have zero power. This point is called the maximum power point. And rather than define the maximum power point, when we talk to other scientists who are researching solar cells, we define what's called the fill factor, which is if we take the ratio of this rectangle defined by the power, the product of the maximum power voltage and the maximum power current, and divide it by the rectangle defined by the VOC, the open circuit potential, times the short circuit current, how much of the big rectangle is filled up by the small rectangle. And it's just a useful number for describing how good a solar cell is to one another. If a fill factor gets to be 90%, then this diode rectification becomes extremely good, and that's a very good thing. In general, you want high VOC, high short circuit current, and high fill factor. Now, a solar cell works on the principle that you shine light in and you promote an electron from the valence band to the conduction band. In organic semiconductors, we call these the highest occupied molecular orbital level, the HOMO level, and the lowest unoccupied molecular orbital, the LUMO level. But anyway, an incident photon with energy lower than the band gap will not be absorbed. And with energy equal to the band gap will be absorbed. And with energy higher than the band gap will be absorbed, but that excess energy is very rapidly lost to thermalization. And so each photon incident with energy equal to or greater than the band gap creates one electron hole pair with energy equal to the band gap. So the energy that you could get out total would be equal to the band gap times the number of photons that are incident with energy greater than the band gap. And so you can use this to estimate what is the very upper limit of an efficiency, of power conversion efficiency from a solar cell that you could ever hope to get. So this is the Shockley quasar limit that was published in 1961 by Shockley and Quasar, and this is largely regarded as the most important solar cell paper ever published. So everyone should be a little bit familiar with it at least. Here I show the incident solar spectrum, and just based on the equation that I showed before, the power conversion efficiency would be equal to the band gap times the integral from the band gap to infinite energy of the solar spectrum, divided by the integral from 0 to infinity of the energy times the number of photons incident with that energy. So this is the incident power divided by the power that you can get out divided by the incident power. And just that assumption alone says that you could have a theoretical maximum efficiency of 44% power conversion efficiency at a band gap of 1.1 eV. But everything emits light also. So everything that absorbs light also emits light and through black body radiation. And so any solar cell is absorbing light from a small solid angle subtended by the sun at a very high intensity, but it's emitting light over either 180 degrees or 360 degrees if you don't have a back reflector contact. And so you wind up with the diode equation. So the incident, the short circuit current is equal to the absorption of your semiconductor times the flux incident from the sun. But your diode equation has this J0, so your dark current is proportional to that same absorption coefficient times the radiant flux of your blackbody radiator at a given temperature. So your VOC, the maximum VOC that you can hope to have, is limited by the ratio of the short circuit current divided by J0. And the way you can make your solar cell eventually reach that 44% limit is through concentration. So if your JSC becomes much, much higher than J0 through either concentration, which increases the intensity, or you can imagine it increases the solid angle that the solar cell sees the sun over. So at one sun intensity, if I just take a solar cell and put it on my roof, the maximum I can hope to get from a single semiconductor junction is 32%, not 44%. And that's at a band gap of roughly 1.3 eV. But with organics, we have a slightly bigger problem. When we shine light in, we don't generate free carriers. We have an extra loss mechanism. We promote an electron from the HOMO level to the LUMO level, but that is immediately formed into a tightly bound exciton on the order of 100, 200 MeV binding energy. So it's much higher than thermal energy. We can't dissociate them easily. We need some external process. And so this is the heterojunction, the photoreduced charge transfer that I described earlier with the fullerenes. So you create an exciton, you dissociate the exciton at the interface, and you harvest the electron in the hole, but now no longer at the optical band gap, but at the transport band gap, so the effective band gap. This energy loss is very significant. I'll get back to that in a minute. So aside from the energy loss, we have one consideration to take into account. We shine light and we generate an exciton in the bulk of the semiconductor. That exciton has to diffuse randomly to an interface before it can dissociate. And that diffusion length is less than 10 nanometers. There's some debate about exactly how big it is in each material, but we can assume 10 nanometers is about the upper limit for the most part. So this domain size has to be on the order of 10 nanometers, but a 10 nanometer thick film doesn't absorb very much light. So we make what is called a bulk heterojunction, where we blend the two materials together, and they phase separate into domains on the order of 10 nanometer size. And then we need to induce an electron transport layer, so hole blocking contacts and hole transport layers that block the electrons to prevent just shorting of the device across the two electrodes. That energy offset that I showed before brings our heterojunction efficiency limit down from the 33%, 32%, down to closer to 15%. So here we have some 17%, and this is assuming everything else in the device is exactly perfect. So that energy loss, that energy offset, brings us very far below what we would ever hope to get in terms of maximum power conversion efficiency. And so where do we stand now in 2015 with organic solar cells? So the efficiency record for an organic solar cell, which uses a polymer and a fullerene, like I showed before, not the same polymer, not the same fullerene, is 11% power conversion efficiency. And that's not too far off from the maximum 15-16% that we might eventually be able to get. And once we have an efficiency, we're concerned with what are the device stability, how long will it last, and how much does it cost. And so a reasonable cost estimate for organic solar cell devices, assuming certain parameters for scale-up, is on the order of 65 cents per watt peak. And the stability estimates of commercially available modules now is on the order of 5 to 10 years, but they were not really made 10 years ago, so we have to kind of extrapolate what their degradation lifetime might be into the future. That's just where we stand now. But moving forward, we want to consider alternative metrics for how good a solar cell is, because how well it performs is not the only thing we have to consider. We also need to consider how flexible and how much does it weigh. We have to consider how toxic is the material, how recyclable is it, and we need to consider how scalable is it. Can we scale it up to extremely large size if we really want to make a lot of power from it? And that brings me to the next question. The The real motivation is not how good are the devices, but what are they good for? So there are some alternative applications, including on-skin monitors or displays or photosensors or power generators, remote travel, new form electronics, things that we haven't been able to make before, things that we haven't even thought of before, lightweight robotics and these types of things. And one particularly quite good application that you might want to use solar power for is to make a lot of power. So making a lot of power is kind of the goal of solar energy, because if we really want to replace coal or oil or natural gas or something, then we need to make a lot of power from solar energy, if not other sources. So right now, the world uses roughly 17 terawatts of power that's projected to grow, or at least double, maybe by 2050. But if we want to make, let's say, 10 terawatts of power from photovoltaics as our target, then I would argue that we really need to compete with coal and natural gas on the cost standpoint. And the reason is, if you look at just the economics, in 2012, the entire world GDP was $72 trillion, and the entire world energy consumption was roughly 160 trillion kilowatt hours. And simply dividing those two numbers gives you the very upper limit for what we could spend on energy. That number works out to be 45 cents per kilowatt hour, which might be depressing if you look at your electricity bill, and it's only a factor of 3 off from that. But historically, in the United States, if we look through, the energy spending as a function, or as a percent of GDP hovers between, let's say, 5% and 15%. But when it approaches or exceeds 10%, those are times of economic crisis in general, so 2008 and the late 70s. And in the mid-90s, when times were free-flowing, we had much lower than this. So let's put 10% of GDP as our target average energy cost. And so our target average is 4.5 cents per kilowatt hour. And the current price of coal and natural gas is 1 and 2 cents per kilowatt hour. So if we want to produce power on an average cost of 4.5 cents, we really need to have a big source of production that's cheap. And if we want that to be PV, we need these to be our cost targets. So, assuming some reasonable device performances, the incident power from the sun is roughly 1,000 watts per meter squared, and the capacity factor that accounts for the fact that there is night and day, winter, summer, clouds, rain, shine, snow, all of the above. So if we assume a module efficiency of 15% power conversion efficiency and a module lifetime of 25 years, then the total energy we can get from 1 meter squared of solar panels is 69,000 kilowatt hours, or 6,900 kilowatt hours. And if you multiply that by 1 cent per kilowatt hour, that means we can afford to spend $69 per meter squared at the direct coal equivalent cost. But if we want to build millions of square meters of these, somebody has to pay for them, probably a bank, and the bank will want to give us a loan and expect interest in return, so our real acceptable cost at the coal equivalent is $54 per meter squared. Now that is cheaper than a concrete patio you would put in your backyard. The current cost of PV installed is about $750 per meter squared, which is about 10 times too much for real large-scale power generation. It's cost competitive if you're doing residential solar. And so this article appeared in The Guardian last summer. It says solar has won. Even if coal were free to burn, power stations can compete. That might be true for the residential end user, but for real large-scale power generation, we're still very, very far off. And one additional aspect is that if we do want to make 10 terawatt solar power plant, given our capacity factor, we would need to have 50 terawatts, or close to 50 terawatts of peak solar power production. Assuming a panel lifetime of 30 years and a module efficiency of 20%, which are kind of dream numbers at this point, we would need to produce 1 kilometer squared per hour forever to replace the solar panels that are dying at the end of their cycle. So that's a large-scale power plant production. So we really need to be producing large amounts of solar panels forever. And if those solar modules are 2 centimeters thick, like the ones you see on your roof now, then we need to be producing the same volume of solar panels as we currently produce of Coca-Cola. And the cost is roughly 3 times the cost of Coca-Cola. The acceptable cost is roughly 3 times that of Coca-Cola if it was all produced in cans. So For photovoltaics, for large-scale power generation, we have pretty lofty targets. So we definitely need 15% module efficiency, and in order to get that, we need roughly 20% module efficiency. So in the long term, the theoretical maximum of about 15 or 16% cell efficiency for this heterojunction organic solar cell structure is insufficient for many reasons. Our cost targets, though, under $60 per meter squared installed cost, organics are one of the more promising technologies. So there's a little bit of a dichotomy. So we might want them because of the cost, but we don't want them because of the efficiency. And this has always been the story with organics. We definitely need 20-year module lifetime, and we will need 1 kilometer squared per hour production of the material. So real large-scale, flexible roll-to-roll processing is not just nice, it's necessary if we really want to produce something real. So now moving on from background to a little bit of my results over the past maybe 10 years or so that I've been working on these materials. When I started working on them in 2005, one of the biggest knocks on the material was that the efficiencies had just started to come up to respectable values. But if you remove them from a nitrogen-filled glove box, the devices would die within minutes. And so this 30-year module lifetime seemed like a complete fiction. Even though the efficiencies were just starting to become real, this was one of the biggest issues. And if you look at the conventional device architecture, at the time, calcium and lithium fluoride and aluminum as the metal back electrode were the most common materials used. And these aluminum, and especially calcium and lithium fluoride, are extremely air sensitive. So these are the materials that would react within minutes. And so what we did at first was we wanted to replace this with something significantly more stable. And I'll present some results here that show that we've used zinc oxide, more recently this cross-linked polyethylenimine, with some reasonable success. So at first, we used zinc oxide, and we produced it from a solution of zinc acetate, which requires annealing at 300 degrees C to convert it to zinc oxide, which means that we can't put it on top of the polymer because the polymer would burn away. So we put the zinc oxide underneath, spin-coated the polymer fullerene blend, and capped it with a silver layer. And because now the electron transport layer is on the bottom, we call this an inverted device, a name which has stuck and become very popular. And so this device, back in 2005, we made the devices and reported in 2006, produced a 2.5 to 3% power conversion efficiency solar cell, which is at the time state of the art. And it was a completely different device architecture using the same active layers. And so this kind of spawned a revolution in terms of finding different device contact layers that improve the stability. So here we see that the device works on par with what previous devices had. But the real interesting part is that if we subject these devices now to a shelf life durability study, the zinc oxide devices not only outlast their conventional counterparts, but they improve significantly upon exposure to air. So by replacing this air-sensitive device, we were able to make devices that we could store and use in the lab for all kinds of purposes for years even. So here we show this up to about a month, but we can make devices and store them in the lab for about a year, and they work as well or better than they did when they were fabricated. Shelf lifetime is not so useful though, because if you shine light on this, zinc oxide is a wide bandgap semiconductor that's a little bit photocatalytic, and it causes some other degradation processes, and it kills the device anyway. So it's not perfect. More recently, we've used what's called polyethylenimine, which is an amine-containing polymer. And this is an insulator, so you have to put down a very, very thin layer, sub-monolayer, maybe 2 nanometers or less of this material. And we cross-link it onto the surface, and then we can subsequently solution process any layers on top that we want. We cap this with the molybdenum oxide silver back contact, and we wind up with a very reproducible way of making devices with very high fill factors. These devices with polyethylenimine are similarly much more air stable than their conventional counterparts. And the reason that this works is that the polyethylenimine introduces a contact potential dipole, bringing the effective electron affinity 500 millivolts closer to the vacuum level, making it much easier to add and remove electrons from the LUMO of the fullerene. So you can use this on almost any oxide or metal surface to render it an air-stable electron selective contact. some significant improvements in terms of the weight and flexibility of these devices. One of the biggest advantages, or the most often claimed advantages of organic photovoltaics, is that they are thin films, and so they are lightweight and flexible. But I showed you this picture here several times before, but even for this flexible organic solar cell, which is from the ECN in the Netherlands, if I draw this picture to scale, everything is the substrate. Everything interesting and electronically active is contained in this purple thin line at the top. The solar cell itself consists less than, or roughly 1% or less of the total thickness and of the total weight of the solar cell. So if we want to improve the mechanical properties of the solar cell, we just need to look at what substrate we're building it on. And so one thing we could do is we wanted to try to replace this plastic with paper. It's highly recyclable, it's highly compatible with printing and all kinds of processes, but that presents two problems. And these were problems that were investigated and largely solved by my postdoc, Lucio Leonat. And paper is very porous, so it absorbs any solution you put on top of it like a sponge. And it's also not transparent, so we have to put the transparent contact on the very top. And so here, what we've done is we've glued on a foil, a zinc-coated foil. And this is the same process as if you are making a beer bottle label with shiny foil on top. This is cold foil lamination. It's a very well-known printing process that puts down these metal electrodes. The zinc has a little bit of native zinc oxide on it, but we can't heat it up to 300 degrees. So instead, we just coat that zinc oxide with polyethylenimine as reported above. So here we have zinc as the conductor, a little bit of zinc oxide, but not very well controlled, and then coated with PEIE to make a nice reproducible electron selective contact. We then use a polymer fluorine layer and cap it with a 3-layer molybdenum oxide, silver molybdenum oxide transparent top contact. Here the molybdenum oxide is only about 10 nanometers thick, and the 2 layers are used as electron blocking hole selective and for index of refraction matching to the air. And in doing so, we were able to make paper-based solar cells that are 4% efficient. But that polymer fluorine combination should give us roughly 9% power conversion efficiency on glass. And the real reason that it doesn't is that that transparent top contact is not particularly transparent, especially in the peak absorption region of that polymer. So there's a lot of work for improvement there. But there's also a question, if we have a piece of paper and we glue on a plastic foil with some zinc on it, why do we need the paper? And so if we're looking to really minimize the weight and maximize the flexibility of the devices, we want to use the smallest, thinnest substrate we can possibly think of. And what we found was a 1.4 micron thick mylar foil that's produced an extremely large capacity. It's made for foil capacitors. The smallest quantity we could buy is a 10 centimeter chunk of the roll that they cut off at the end when they're processing them. They would throw them away typically, but then they send them to us for free. And it's 10 centimeters wide and 10 kilometers long. So you get one roll that will last you forever, you'll never run out. And on top of this, we process the solar cell that's made with polymer, transparent conducting polymer electrode, using P3HT, which is a standard organic photovoltaic polymer, and PCBM, which is a very standard organic photovoltaic fullerene acceptor, as the bulk heterojunction layer. And we cap it with, unfortunately, calcium and silver, which is not very air stable. So these devices were not particularly air stable. And the first question is, does the substrate itself affect the performance of the solar cell? And you would hope that it doesn't, because it's just an insulator that holds things together. And in fact, it doesn't. If you build the devices on glass or on ultrathin foil, you wind up with basically a 4% efficient solar cell either way. And if the devices are small enough, resistance in the P dot layer being the limiting factor, the devices are essentially the same performance as you would get on ITO-coated glass too. So there's not really much difference in terms of performance. But what do you gain? What's the point? Well, you've eliminated 99% of the weight. And so sometimes power per unit area, which is equivalent to the power conversion efficiency, is not the most important metric. If you are backpacking in the wilderness by yourself, you have more area than you could ever use to fill up with solar cells, but you have to carry them in yourself and probably carry them out yourself. So you want something that's very lightweight and very flexible. And this roll that's 10 kilometers long, I could carry it in and out and up and down mountains, it's no problem. So you can think of it for all these other, balloons, these weather balloons, these artificial flight skins, all these kind of things. they might have much better applications. So there's this alternative metric that's called specific weight, which instead of power conversion efficiency is the watts that you get out per kilogram. And if we compare, we have a 4% efficient solar cell, so we get roughly 40 watts per meter squared peak out of the device, but at 4 grams per meter squared, we wind up with 10 watts per gram, which is quite, by far, the highest power per watt from any photovoltaic technology ever, with a pretty rudimentary organic photovoltaic device. Now we make these devices, so I'm going to show you a video that was made for Japanese national television. It works, okay? We make these devices by sticking them to a support, whether it's a wafer or a piece of glass. Then we peel them off when they're done. And I'll show you, you can see just how lightweight they are when they fall down. You can see how flexible they are when he bends them around. She's not a scientist. This is Martin Kaltenbrunner. He was the Ph.D. student who worked with me on this project in Linz, and after he graduated, he went to Takasu Mei's group at the University of Tokyo, and that's where they filmed this video. So in addition to weight, we've gained a lot in terms of flexibility. When you bend something, whatever's on the outside tends to crack apart, and whatever's on the inside tends to compress together. That's called bending strain. And to first order, it's quantified, the bending strain is quantified by half of the thickness divided by the radius of curvature at which you bend it. And each material will break at a critical strain. For organic photovoltaics, and this is based on results from 2006 from my institute, Linz Institute for Organic Solar Cells, in combination with Mike McGee's group at Stanford. If you have a 125 micron thick substrate with ITO-free electrode like we have, their critical radius was somewhere less than 5 millimeters. So by shrinking the thickness by roughly a factor of 100, we estimate that the critical radius would be about 50 microns or less, which we tried to demonstrate originally by wrapping the solar cell around a human hair with a radius of 35 microns. That's very difficult to do. It's also not particularly quantitative. So instead, we tried to subject the solar cells to the most extreme form of deformation we could possibly think of. What we did was we took an elastomer, it's basically a rubber band, we stretch it, we glued the solar cell onto it, and we relax the elastomer. And in doing so, it forms a random network of wrinkles and folds that are really brutal looking. And then we can re-stretch and recompress the solar cell as we please. We define an effective stretching strain as change in length over length, compression being normalized to the flat state, and tensile strain being normalized to the minimum length over which you compress it. So here's an image just showing what the flat solar cell looks like, and as you compress it, it forms these wrinkles and folds. Those aren't cracks, those are just folds in the solar cell. Here you can see the solar cell stuck on the elastomer, and we pressed it out of the plane so you can get a nicer view. And this is a close-up SEM of some of those wrinkles and folds. You can see that most of the area is flat and safe, but there are some wrinkles that are tightly bent radius, and some points where the radii come, or where the wrinkles come to a junction, which are very sharp. And those are likely the formation nuclei for cracks, which cause the ultimate degradation of the solar cells, which I'll get to in a minute. Here's just an image showing that we can compress and then stretch and compress and stretch the solar cell over and over again. These aren't cracks, these are just wrinkles that haven't fully been stretched out because of the viscoelasticity of the elastomer. So as you compress this device, does the solar cell still work? This was the first question. So the most probably impressive result is that it works exactly the same. It even works a little bit better. So when you compress the area, you have less incident light, so you get less photocurrent you can see. But when you re-stretch it, it goes back to this dotted black line, and it works exactly the same. You can see here the photovoltaic device parameters, the short circuit current, the VOC, the fill factor, and the power that you get out of the device, plotted as a function of the compression ratio. And the solid black line is what we would expect based on the incident area change. And the power always tracks slightly above that. And that's simply due to the fact that when you're putting less current through the resistor, you get less voltage loss in the resistor, so you get slightly better power through the device. And then we can compress and stretch and compress and stretch the device repeatedly over and over again, and see that the device still performs reasonably well up to 25 cycles of stretching and compression. As I mentioned before, an LED is not so different from a solar cell. So to manufacture LEDs on this technology is as simple as removing the P3HG PCBN and replacing that with a single light-emitting polymer. So in this case, we used either this in-house synthesized what's called ANEPV stack, which is an anthracene-containing PPE PPV polymer, or just this commercially available MDMO PPV, which emits orange. So here we have a bright red emitter, and here we have an orange emitting polymer. We made two different colors at the request of the reviewers. So the current voltage and the intensity, light intensity voltage curves of the LEDs are shown here. Both devices, both colors reach an intensity threshold of about 100 candelas per meter squared, which is about what you would need for an indoor display application, dim indoor display applications. They're not particularly bright, but they are functional. And here you can see the two spectra coming out. Here I plot the two colors on the XY chromaticity diagram, and you can see here one of the red LEDs operating in what I call freestanding foil configuration, where this foil is just floating by itself. So the mechanical deformation of these LEDs, we can literally crumple these LEDs in freestanding foil configuration as much as you want. I have it suspended in the top row between two pieces of glass, which I then bend and twist and crumple. But you can peel off the bottom piece of glass and crumple the LEDs between your fingers just like a tissue, and they work just fine. There's no deformation whatsoever, no damage. If you rip the device, it will rip in an instant because it's a very thin film. But from crumpling, no problem. We also put the LEDs on the same elastomer, compress them and stretch them, and I've compiled that series into, a, here we go, a stop motion video. So you can see on the right the edge of the elastomer and the device compressing and stretching. And I submitted this and the reviewer said, that's great, you can make the pixels blink. So we made another video where the pixels blink, which is just driven by an external relay, but it was only about 2 weeks worth of work. So you can see them operating under compression and stretching. So using this deformation technique, we've made a network of wrinkles and folds, but these folds can give us an idea, a better idea, for what the radius of curvature that we're subjecting these films to before suffering complete damage. So we take what's called a 3D optical microscope, and so you scan the focal plane and measure the height of the focus of each point, and you get a height map of the film over a large area. So we have height as a function of x and y, and we can fit, here I wrote the equation for fitting a curve, but we can fit a sphere to the surface of each point and estimate the radius of curvature at that point, and I plot that here. And in doing so, for each stage of compression, we can compute a histogram of what the radius of curvature is at various points. And most of the films is flat at any given compression, but there's always a little bit that is compressed very tightly down to radius of curvature, let's say 10, 20 microns or less. And we plot those here in these blue dotted lines, or these blue squares here. At roughly 45% compression, 20% of the film is compressed to a radius of curvature of 16 microns or less. So we've made extremely flexible, stretchable, and lightweight LEDs and solar cells. So this brings us to the next question is, we've made solar cells and we can make lightweight and high volume because they're extremely thin, maybe compatible with extremely high throughput, but if they'll never exceed the 15% power conversion efficiency, who cares, right? If they won't get there, if they won't get to our targets, then what are they really good for in the end? In this process, I showed you this diagram before, this energy associated with dissociating the exciton is a significant cost, and it's actually an unacceptable cost in my opinion. If somebody proves me wrong, I'd be glad, but as of now, I believe that that is the fundamental process that we cannot accept in terms of making large-scale organic photovoltaics. And so I want to present briefly one of the most promising things I've seen in a long time in terms of what we could do and what we can look for in new materials for making direct photoexcitation of free charge carriers in organics. And that is looking at hydrogen-bonded pigments as semiconductors. And this is the work of one of our Ph.D. students. His name is Eric Blowatsky. He graduated actually in late 2013. And here we compare two hydrogen-bonded pigments, pentylidione, which is a yellow inkjet toner in Epson printers, and quinacridone, which is a magenta inkjet printer, but it's also pink hair dye that's produced in extremely large commercial quantities. And if you look, these are both, so this is a 5-member ring, kind of analogous to pentacene, and this is a 4-member ring, kind of analogous to tetracene, but the presence of these amine keto groups completely blocks the intramolecular conjugation as described before. So now our conjugation is basically limited to one benzene ring along these molecules. So from an initial eye test, you would look at these molecules and say, those are not going to be good organic semiconductors. Let's not look at them. But we did look at them. And one of the reasons is that similar to the TIPS pentacene that we presented before, the hydrogen bonding causes these molecules to form long chains of planar molecules. And then those chains sit right on top of each other in what's called brick-in-the-wall configuration. And so we have very cofacial and very tightly packed molecular crystals of these guys. And both quinacridone and pentylidione, when you go from dilute solution to thin film, you go from essentially monomer crystal or monomer molecules to crystalline films. You see a very strong, over 50 nanometer shift in the absorption, the red. And that's part of the definition of a pigment as opposed to a dye. A dye is a molecule that absorbs light. A pigment is a molecule that absorbs light based on its crystal structure. So if you pack it into a crystal, it absorbs light depending on the crystal structure as well. And so here we have these pigments that show a strong chromic shift when they pack into crystals. But do they perform as semiconductors? And we made transistors, and if you look at the transistor performance, comparing tetracene to a pentylidione, that 4-member ring, has a mobility of roughly 1 centimeter squared per volt second, which is very high for organic semiconductors. Quinacridone is slightly lower than pentacene at about 10 to the minus 1. But if we look at the stability over, this is a plot over 6 months, both the pentylidione and quinacridone are rock solid. They don't degrade whatsoever, whereas pentacene and tetracene degrade very, very quickly. So here we plot the mobility and the on-off ratio of the transistors. This was the data that we had at the time we submitted the paper, but now it's been almost 2 years and they're still rock solid. They haven't degraded at all. You can take the same devices and run them underwater, doesn't degrade at all. pH 2 to pH 11 doesn't degrade at all. They work just fine. So we have rock solid semiconductors. If we plot them on, here we plot mobility of reported organic semiconductors as a function of the T80 decay lifetime of devices from the literature. We can see that these molecules that don't look anything like organic semiconductors are actually among the best performing and the most stable organic semiconductors reported anywhere in the literature. So this is really surprising. But that by itself is not directly applicable to solar cells. We have something that's high mobility, is stable, that's good. It's also extremely cheap. So because quinacridone is produced commercially for dyes and pigments and car paint, you can buy it for 30 cents per kilogram, which translates to about 3/1000ths of a cent per meter squared, so it's extremely cheap. But it also produces photocurrent by itself. You don't need a heterojunction. So if you put this material, if you put pentacene between an ITO-P dot electrode and an aluminum back contact, you get, just like in about every other organic semiconductor, you get about 10 microamps per centimeter squared of photocurrent. But if you put quinacridone in, you get over a milliamp. So you have 15 or 16% external quantum efficiency from just quinacridone by itself. So the same phenomenon that's causing this, this crystal-induced color change is causing a delocalization of the excitations, which means we can easily, if not freely, excite photocarriers without a heterojunction. And we can, by varying the metal, here we used only gold, silver, and aluminum, we can tune the VOC of this device up to well over a volt, which is very, very high for an organic photovoltaic device, and we have no heterojunction. So sort of summarize, we've demonstrated air-stable electron transport layer. We've changed the substrate to change the mechanical properties, and we see new semiconductor materials that show that if we can arrange or control the intra or intermolecular interactions in ways other than just simply putting them down and having them pack in a van der Waals configuration, then we might be able to use organic semiconductors to make solar cells. This solar cell was about 1% efficiency, but we might be able to approach 20% if we can get rid of that heterojunction offset. And that is going to be key. So with that, I would like to thank my collaborators in VINCE, whether in our institute, visitors, or from the soft matter physics group, our funding sources, my other collaborators, and thank you all for your attention.
Thank you very much. That was a wonderful presentation. If there's any questions from the audience, if there are any questions from the audience. And Luke.
So you mentioned the Shockley-Schweitzer paper, which gave an overall limit to efficiency. That's for single band gap.
Single junction, single band gap semiconductors, yes.
Do you have ideas for combining thin film, cheaply produced organic solar conductors into multi-band gap systems where you have layers and stuff? Sure.
That's a almost commercially available product, actually. So if at the very beginning, I showed a plastic roll that had some pink stripes on it. That was the first commercially available organic solar cell, which was just a single junction polymer solar cell. But now there's a company called Heliotech, which does evaporated small molecule devices. But when you evaporate sequential layers, it's relatively easy to stack them on top of each other. And so in doing so, they can fabricate modules with efficiency of about 13%, or no, 12%, which is very, very good. And they report some of the highest stability. So yes, you can do that, and it does work. It's still not 15 or 20% efficient. It's still only 10 to 13%, but it's a very good idea, very promising idea.
Does it play into what you're trying to do? Would this then feed into that same mechanism?
No, the multi-junction cell is a question of processing. If you can make a very efficient single-junction cell, you just stack multiple efficient single-junction cells on top of each other. So it's like having several devices occupying the same space with a wide band gap followed by a mid band gap followed by a narrow band gap cell. So. Yes?
Has your early zinc oxide work published?
Yes.
Could I have the reference?
Yes. It's Applied Physics Letters 2006.
I'll
just give you the paper, okay? Yeah. Yes?
Also look, your video showing you have a flip pixels. How big are they?
The pixels that I showed are 3 millimeters by 5 millimeters.
Those 3 by 5.
They're large pixels.
They're large.
And that's because we have a set of standard masks in the lab. It's just limited by the mask size. So I could change the masks and change the pixels, but that's our standard configuration in the lab.
I have another question. You're talking about the solar cells, which means you generate a current. What is the difference compared to solar cell perspective versus the photo detection perspective?
So a photodetector is often, the metric for a photodetector is the signal to noise. So oftentimes it's beneficial to operate a photodetector in strong reverse bias because then you can extract all the photocurrent and measure the on-off. You can operate it in a photodetector in photovoltaic mode, but it's often beneficial to apply a bias and get better signal to noise. So. Yes?
This last part of this material, and then it ended up with a solar cell that wasn't very efficient. So why wasn't that?
So the reason it wasn't very efficient is because these things form big crystals. And we're trying to make thin film devices, and when you have a layer in your thin film, so you have two contacts with something that doesn't form a nice film. You have big crystals with holes in between. And so you're limited by the shunt resistance from having the two contacts that touch each other directly in parallel to the actual crystal itself. That's one of the reasons. The other reason is that the band gap is not optimal by any means. But that same material, if you could make a very good film out of it, might give you a 5 or 6% efficient solar cell by itself. And then if you did some molecular engineering or bandgap engineering, you could derive the same physical property that causes it to work into a very efficient solar cell, hopefully.
So, has anyone looked at, I assume that the emission spectrum of this molecule is well studied, right?
It's
So-
mediumly studied, not well studied.
So, so you mentioned that you no longer have to deal with excitons here. I assume that what you mean is that the binding energy of the exciton is expected to be really low, right?
Yes. We measured it at roughly 5 MeV through a pretty crude photocurrent measurement at various temperatures.
So, okay, so you don't see any, but presumably if I cool this down, I could see excitonic emission,
Yeah.
let's say, right?
Yeah, and I didn't show the luminescence here, but in a typical molecular semiconductor, here, you'll have some an absorption peak and some vibronic peaks, and the luminescence will look like a mirror of this absorption about somewhere near the band edge. And in these systems, this in the video not so much, but in this quinacridone we see a little bit of the mirror signature, but you see a broad band emission into the infrared, which is kind of indicative of an excimer state, although it has not been well studied. So we've seen it, but we haven't
But
studied
that's
it
not
well.
single crystal data, is it?
No, that's thin film data. Yeah,
Okay.
we have, and it's also very easy to grow single crystals of this material. So, Adam, you showed me your train sublimation. You can grow crystals almost as big as your rubric crystals using this material in the same system. So.
Have
Yes.
you tested your films in water? Are they stable? Like after you
The films of these devices are stable in water. Yeah. The devices are stable in water. So you can
I was
operate
wondering
them.
that we have zinc oxide in your films.
Yeah, those devices are not stable for water. Those are not stable.
Any other questions?
Yeah.
No.
You mentioned briefly these cells tearing. Is that practically an issue that would concern someone when you're trying to apply these things?
It really depends what you want to do with them. From a manufacturing and handling standpoint, it was fine. If you can cut them with scissors easily, you can rip them easily. If you rip them on accident, you'd probably be upset about it. The real problem with them is actually thermal management, not physical, because if you have an LED and you drive current through it, you only get about 1% of the energy comes out as light, the rest is lost to heating, and there's no mass, so it heats up very quickly. And if you try to operate the devices in freestanding foil very bright, they burn. They heat up to 180 degrees and melt the polyethylene that supports them very quickly. So that's more of a problem, I would say, than the tear.
You need a heat sink, that's flexible.
Or we could use them here in Vermont, it's cold.
Any other questions? All right, let's thank Professor White again.